Welcome to The Explainer. Today, we are going on a wild ride. We're going to follow a single tiny piece of data, a packet, all the way from your computer, across the entire internet, to its destination, and all the way back. And the craziest part? It all happens in less than the blink of an eye. Think about it. You click on a link and poof, a website just appears. It feels like magic, right? But it's not. It's actually this incredibly fast, super complex relay race that's happening completely behind the scenes. So what is really going on under the hood? All right, so our journey kicks off with something you do a million times a day. You decide to go to a website, let's say www.cisco.com, and you click the link. Now your computer has a goal, but, a name isn't enough to send a letter across the world. It needs an actual address. See, to send this message, your computer can't use a friendly name like Cisco. It needs a specific numerical address. And that's where the domain name system, or DNS, comes in. You can literally think of it as the internet's giant phone book. Your computer asks a DNS server, hey, what's the number for www.cisco.com? And the server looks it up and sends back its IP address. I mean, can you imagine if we had to memorize those long strings of numbers for every website we visit? No way. Awesome. We've got our destination IP address. We know where this thing is going. So now it's time to actually prepare the message itself, your request to see the web page for its very long trip. Just sending your raw data across the internet would be like tossing a single piece of paper into a hurricane. It's just not going to work. It needs to be packaged up properly. And in the networking world, this process is called encapsulation. It's all about wrapping our data in these protective, informative layers. The best way to think about it is like you're preparing a package for international shipping. First, your data gets put into a little box. That's called the TCP segment. Then you slap the main shipping label on it with the to and from IP addresses, and now you've got yourself an IP packet. And then finally, you add the local delivery info, just for the very first part of the trip, creating what's called an Ethernet frame. Every single layer is like another envelope, getting it ready for a different leg of the journey. Now, that TCP layer we just mentioned, that's really important. It stands for Transmission Control Protocol, and you can think of it like choosing certified mail with tracking. TCP is all about reliability. It triple checks that every single packet arrives, that they're in the right order, and that there are no errors. Now, the alternative is UDP, which is kind of like sending a postcard. It's super fast because it doesn't bother with all that checking. So you definitely want TCP for something like downloading a file where every bit matters, but UDP is perfect for a video stream or a phone call where a tiny glitch you don't even notice is an acceptable trade-off for speed. So our message is perfectly packaged, it's addressed, it's ready to go. But before it can hit that global internet superhighway, it has to navigate its own neighborhood first, your local area network, or what we call a LAN. And a LAN is, well, it's pretty much exactly what it sounds like. It's the private network inside your house, or your office, or at school. It's all the devices right there in one building that are physically connected and can talk to each other directly. And how are they talking? Physically, our little packet is now traveling as tiny electrical signals or pulses of light. It might be zipping through a normal copper cable, which is super common and pretty cheap. Or if you need some serious performance, it could be traveling as a beam of light down a fiber optic cable, which gives you incredible bandwidth and isn't bothered by electrical noise. But yeah, it's a bit more expensive. Okay, for this local part of the trip, two addresses are absolutely critical. We've already got the IP address. That's like the main street address for a big office building. But to get a package from the front door of that building to the right person's desk, you need their name, right? Well, that's the MAC address. It's a unique ID burned into the hardware of your device. So remember, the IP address gets you to the right network, but the MAC address gets you to the right device on that network. The device managing all this local traffic is called a switch. Think of the switch as the mailroom clerk inside our office building. It looks at the destination MAC address on the incoming frame and smartly sends it only to the one port that's connected to that specific device. It's so much more efficient than just shouting the message down the hallway for everyone to hear. Our packet has successfully made its way through the local network. It's arrived at the edge. It's at the front door of the building, ready to be sent out into the big wide world. And this is where a truly essential device takes over. And that device is the router, often called the default gateway. A router is basically the internet's traffic director. Its job is to connect different networks to each other. It takes one look at the destination IP address inside the packet, checks its map of the internet, and makes a split-second decision about the best path to send the packet on for the next hop of its journey. Now, to keep all this traffic from turning into total chaos, large networks are broken up into smaller, more manageable pieces called subnets. It's a lot like how a city is divided up into different zip codes. It makes getting around way more efficient and cuts down on all the unnecessary traffic. I bet you've probably seen an address that starts with 192.168 before, right? Well, these addresses you see here are special ranges that are just for private networks, for our local neighborhoods. They can be used over and over again in millions of homes and offices all over the world because they never go out onto the public internet. They're like local street names that only mean something inside your own town. So you might be wondering, how do all these devices with their private, non-unique addresses actually talk to the internet? Well, it's through this really clever service called Network Address Translation, or NAT. Your router basically acts like a receptionist for your entire network. It takes all the requests from your private devices, sends them out using its one single public IP address, and then keeps track of who asked for what so it can deliver the replies correctly. It is a really ingenious piece of tech. After hopping across countless routers, maybe even all over the world, our packet has finally arrived at the destination network. Its amazing journey is almost over, but there are still a few really important steps left. So the destination server now does the exact opposite of what our computer did way back at the beginning. It's a process called de-encapsulation. It just strips off each layer one by one. First the frame, then the IP header, then the TCP header. It's like unwrapping a gift until it gets to the original data inside, your request to see the web page. But wait, before that data is fully accepted, it has to pass one final checkpoint, the firewall. A firewall is the network's security guard, plain and simple. It inspects every single packet that tries to get in, checking it against a list of security rules to decide if it's allowed in or if it gets dropped. It's a critical line of defense. And there you have it. From one click, our packet was addressed, wrapped up, sent through the local network, routed across the entire globe, checked by security, and finally unpacked. It's a process that can involve dozens of different devices, crossing thousands of miles. And get this, that was just the request. The web server then has to do this entire process in reverse just to send the web page back to you. And the most incredible part? This entire round trip, this absolutely bonkers journey of packaging, routing, and unpacking happens hundreds of times a second in a tiny fraction of the time it takes you to blink. It is a staggering feat of engineering. But it also brings up a pretty big question. With all this data flying around at the speed of light, what actually keeps it all secure? We saw the firewall, but what about protecting the data itself while it's in transit? Well, that's a story for another explainer.